Great. Our next speaker is Julian Opperman from CodePlay Software, who's going to be talking to us more about compiling SYCL code. Over to you.
Yes. Morning, everyone. So yeah, I'm Julian working for CodePlay and excited to present some work today, joint work between my team at CodePlay and folks at Intel. So for today, I want to two-part presentation, more or less. Want to talk about the user side of using this extension. This is the first part, and then share some details from the implementation that I find interesting. Then we'll talk about performance results, which was mostly spoiled by Alexei's presentation yesterday, but we'll quickly go over it and then, of course, conclude. So yeah, this kernel compiler extension, before we get into that, let's talk a bit of motivation for runtime compilation. And I think this runtime compilation or online compilation is useful when you have code generated or specialized at runtime. So we can think of maybe template meta programming, or maybe you have a domain-specific language that creates your SYCL code at runtime and so on. So this is where this kind of runtime compilation would be useful. And it's a form of specialization that goes beyond what's already in SYCL, so going beyond specialization constants, for example. Giving a concrete example, think of a gem library like Cutlass or 1DNN, where you have highly optimized implementations that should be picked based on your target device and maybe even on the input shapes of the operation you want to perform. So for this use case, this is intractable to enumerate and pre-compile all combinations of such a kernel, for example. Important note to make, this work is orthogonal to the spectrum of JIT and AOT compilation in SYCL implementations, and also different than what Axel presented yesterday. So in this case, in this talk, it's really about getting new kernels into your application, to the runtime that have not been known when the application or the library was compiled. So it's like a different problem that we are looking at here. The extension itself, kernel compiler extension, is not new. It was presented last year at IWOCL. And you can think of this talk as being the update on the SYCL language support. The extension also supports OpenCL and SYCL kernels to be ingested at runtime. And this is maybe useful if you have like Ninja optimized implementations in SYCL lying around, or want to use OpenCL code with extensions that are not yet exposed to SYCL, for example. So yeah. I think the easiest way to understand this extension is just going through an example. I have 3 slides for this example, but this is all like one source file you can think of, so one application that does use runtime compilation. So let's start with the kernel definition. As you can see, it's a string literal in this case, and it defines a kernel that uses the free function kernel syntax, which is basically a void function that has this markup property. In the range kernel, there's also a property for single task kernels. Next thing to note is the function arguments here are also the kernel arguments of the kernel we are going to define in the order that we declare them here. And this matters because, and this is also one of the motivations why this third kernel definition syntax exists, because, for example, if you have lambda captures, they don't have a guaranteed order, and we will need a guaranteed order later to set the arguments. So yeah, this is part the free function kernel syntax. And lastly, we also need to get the iteration index somehow, and there's another extension that exposes them as free functions, and we are relying on this this extension here to get the iteration ID. Next, let's look at what's the host application for this. One thing to note before is that the extension uses and builds upon the kernel bundle infrastructure, as we will see in a bit. But before we can compile something, we of course should check that our device supports runtime compilation. So there's a query for that. Then we take the source string we just defined and feed it into the create kernel bundle from source function that has been added as part of the extension. And lastly, the former function creates a kernel bundle in the new state X1 API source, and this source bundle we then feed into the build function at number 3 here, and this builds on our source string into an executable kernel bundle. One note I want to make here is that both these functions do take additional arguments and special properties that I'll talk about in a bit. And also, please handle your exceptions. I wanted to keep this example short here, but for example, if you have a compilation error that will trigger an exception, you should handle that and maybe print out the message to the user, do something about that. So yeah, please do keep that in mind. Right, and after we have built the kernel bundle, we have an API, one API get kernel, where we can get a kernel object by name. One important note, you may or may not have seen that in my kernel, I had declared the kernel as X1C, and we will revisit that in a moment, but for the sake of keeping this example simple, yeah, let's just say we can get a kernel back by just using its string name and use that then to work with the normal APIs that have been established in SYCL 2020. Meaning we use our handler to set the arguments by index in order, and then can invoke curl with the kernel object that we obtained from our compiled bundle. Last note to make here is there's no special flags required to compile your RTC-enabled application, so it's just your compiler -fsycl, but in the case of DPC++, to compile and run it. So no special source required here. Okay, yeah, let's have a look at the properties I already mentioned. So these are a way where the application can control the compilation process with these additional properties. The first one is include files, which lets you define like virtual header files that can be included into the source string. For example, if you look at the one circle is that shows an example, and so yeah, these virtual files can be then used by the source string. This is a property that goes into create kernel bundle from source, and I think that's the only one that we have at the moment. The other ones go into the build function. First one would be save log, where you can request the full compilation log, because runtime compiler does not print anything to outer standard error by default, but you can get the log with this property. And as I said, if you have an error, then you will get an exception with a compilation log as well. A bit more interesting maybe is also build options property, where you can pass supported DPC++ options to the runtime compiler. For example, setting a macro in the source string, or also quite interesting, you can add include paths. So if you have a header only library, for example, on disks, then you can also just use an -i build option here to get your header files included into your runtime compilation request. All right, yeah, let's talk about the source code names. SYCL compilation is challenging. Why is that? Because it's based on C++. Of course, names are subject to name mingling. So you probably have seen that somewhere, that namespace names, for example, become this interesting string of characters there, just to make them unique at the lower level where yeah, runtimes operate. So yeah, we want to have our kernels, want to be able to have our kernels in a namespace. We want to be able to overload maybe our kernel functions, and the name then is not, the name alone is not sufficient to resolve these when we want to get it out of the kernel bundle again. And yeah, what about templates? For templates, 1 and 2 also hold. And an additional problem, we also need to ensure that the concrete templates we care about are instantiated and compiled into a kernel that we can get back. Otherwise, just the template definition doesn't really help us much. And for that, we have a force property here also passed to the build function that's called registered names. And this accepts a list of C++ expressions that reference a specific free function kernel. And yeah, this can be as simple as just a like fully qualified name, but as you can, no, it doesn't work. Anyways, as you can see right in the middle, you can use this to distinguish the overloads as well. And the best thing I think about it is you can try all of this out yourself. So the extension, as I just presented, this is included in DPC++ daily builds already, and we also plan to make it part of the upcoming OneAPI 2025.2 release. If you want to try it out, the first QR code takes you to the daily builds page on GitHub, and the second one would take you to the extension document where you can look for like more details on the APIs and the properties and the current implementation limitations that we have. All right. Let's talk a bit about the implementation. So if you think about it, the most naive and most obvious way to do it is probably to just use the existing compiler and invoke that somehow from the runtime. And this is what our first prototype looked like. So the invoke-based implementation, there we would write the source string to a file on disk in a temporary directory, then invoke the compiler as usual, called as an external tool, and then get a SPIRV file out of it and read that back into the runtime, and then finally execute the kernel. A couple of disadvantages with this approach are that there's additional overhead for the file I/O, and it's not just the input and output files, but also the Clangor ICPX is also internally calling other tools via temporary files, so it compounds a bit that you have to read and write from disk. Also, there's maybe a security concern. We do need to find some random file back again in a temporary directory to load the SPIRV from, for example. So not relying on file I/O is also better for security overall. Then to implementation limitations at the time where we looked at this. So there was no suitable on-disk format to get the additional runtime information about SYCL kernels on disk and then back into the runtime, which meant that kernels compiled like this would be like interop kernels, but not feel like real SYCL kernels, meaning things like argument elimination wouldn't work, or properties like required workgroup size would also not be passed back to the runtime. And lastly, there was also a driver limitation that meant we always needed to perform host compilation. So we have also made things slower here. We certainly could have addressed the last 2 points just by improving the driver and define this format, but we thought we could do better and then also address the file I/O related things in one go. And this is what we did with our JIT-based implementation, which is in the focus of this presentation, and also what you will get if you now try out one of the daily builds, for example. So here, the SYCL runtime relies on our JIT library, which links against LLVM libraries and therefore exposes the entire LLVM compiler ecosystem to the runtime. Then we just keep everything in memory, so pass the kernel source as a string, then use a Clang slib tooling interface to compile that string in memory to an LLVM module. And once we have that module, we can use library versions of the remaining steps that the other compilation also had to do, but we can just call them via their APIs. And then get back the kernel SPIRV and can pass on the additional runtime information to make it feel like a real SYCL kernel and give all that back to the runtime and execute the kernel in the end. So what's improved here is all the temporary files are no longer existing, so everything is exchanged in memory. Yeah, we have RTC kernels that behave more like normally compiled SYCL kernels. I want to zoom in on this the tooling step on the next step because I think it's quite interesting. The other remaining things are not so much different than what's happening in the normal compilation, but if you're interested, just talk to me afterwards. Happy to share more details on that. So yeah, for the lib tooling step, it's really cool that this interface exists because yeah, it's offers a really high level interface, and fortunately it works. It worked already with DPC++. So in order to invoke the compiler in this way, we need to do three things. We need to define a virtual file system in which we take the source string and all the files from the include files property, just define them as virtual in-memory files. Because it's an overlay file system, the physical file system is still present, so you are getting a SYCL HPP from disk easily, and also if you use the -i build option, you also get your header library from disk. Then we need to define a compilation command database, which is simple in our case. We only have one source file, and we want to compile that with fSYCL device only, and we pass on any build options that the application gave us with the property. And lastly, we need to pick a tool action, and for that we use the LLVM, emit LLVM only tool action, which only does LLVM code generation, and then we obtain and take ownership of the LLVM module that is produced there, and then the rest of the pipeline is easy to implement. All right, yeah, let's talk about performance. So we were looking at mostly at the overhead that this compilation will incur. So we are using a very simple vector addition kernel to just compare the compilation times between the different implementations. And what we measured on my machine was that, so the invoke-based implementation does 3.5 seconds overall, and the new in-memory pipeline does the same thing, and even more because it supports more features in 1.6 seconds. So yay, 2.2x improvement, but still 1.6 seconds for a simple vector kernel still feels like a lot. So we were in contact with Alexei at some point and also looked closer into what's happening, and we found that almost all of the time is spent in the front end. So yeah, 98.5% in our tracing example here, whereas the other steps in the in-memory pipeline don't really have any significant influence on the overall runtime. And as we've seen all yesterday, parsing SYCL HPP is really the major contributor here. 85% overall, of which 1.5 seconds overall, and one of which 250 milliseconds would be associated with extensions. And the next, the closest contributor after that would be the template instantiation phase, which took 180 milliseconds in my experiment here. And in this case, the sheer number of instantiations is what makes this phase slow overall. So yeah, what can we do to speed this compilation up? We thought a bit about that, and also something we heard yesterday is a question. It would be very interesting for us to use precompiled headers to just process SYCL HPP faster. So if you haven't heard about precompiled headers before, this is basically the AST, abstract syntax tree, serialized into a binary format, which then all but eliminates the costly parsing step. This is supported in Clang, but not yet for DPC++. Yeah, Alexei hinted about that yesterday, that there is some movement inside Intel to implement that at some point, but yeah, it's not available at this point. Then also, as for the talk yesterday, it would be good to modularize SYCL HTTP to just process fewer headers. We probably don't need all extensions enabled by default, and maybe even skip some features like accessors, which don't really make that much sense in context of free function kernels, which we need for runtime compilation. But for this, as we learned, specification work would be required, and also user opt-in or user action at least would be required to not just use the overall SYCL HTTP header, but something closer, something more narrow. But yeah, that would help immensely for this kind of runtime compilation. Then one thing that you can do already today is that is using persistent caching. So it's a infrastructure that the SYCL runtime offers in DPC++, and we just extended that to also work with our runtime compiler. In our case, it caches the LLVM module that we obtained from the frontend invocation. And as you've just seen, this is really gets us the majority of benefits of caching. So we're doing that. And yeah, and I measured for a cache hit. This takes then 150 milliseconds, so 7% of the uncached runtime for the vector example. So still not negligible, but a significant improvement overall. Yeah, and that's basically it. What I would like you to take home from this presentation is that this runtime compilation extension, it extends SYCL's toolbox for runtime specialization. For example, if you want to wrap a header-only library and only instantiate your templates that you need on demand, if you want to generate the best kernel for a given input and a target device at runtime, or maybe if you have like a domain-specific language or accepting user code to be fused into your kernel template, something like that. This would work well in our framework here. But overall, this is really more generic and more powerful than the existing specialization approaches. But as you have seen, it's also more heavyweight. So no free lunch here, but it's just another tool in the toolbox, I would say. Yeah, I've talked briefly about the implementation. You have seen it's really implemented as a thin layer on top of the existing DPC++ code base, which means that we don't really expect any limitations about which kind of kernels you can compile at runtime. If it works in DPC++, it should also work in the RTC setting. And lastly, yeah, as I said, it's implemented, it's available to play around with in the open source release, and hopefully also then in the upcoming One API release. So yeah, try it out and let us know what you think. Thanks.
Hi, thank you. I see two issues with that approach. One is that obviously you're breaking type safety, and there could be lots of that. It's a foot gun, right? If you introduce separate source again. And the other is, as you had mentioned, the compile times. And I think both could be solved by doing necessary specialization work inside at the IR level. And I think that probably most of what users can do could also be accomplished with some extensions to specialization constants that we could expose within the single source fashion, within the single source model. For example, adaptive has an extension that allows you to at time replace function calls in your device IR with function calls to other functions or sequences of function calls to other functions, which basically allows you to completely change the way that your kernel operates. Have you looked into something like that? Because that would solve the most fundamental issue with compile times and all of that, because the front end is gone.
We have not looked into that. So my mental model really is this kind of like Cutler's kernel compilation, where you can't recompile the kernel, and it doesn't really make sense because you want to have all the compile time specializations happening at the template level and so on, which you can't precompile. And yeah, it's about getting new kernels into the runtime. So I don't see how. I mean, of course, you could probably do more specializing existing kernels, but at some point you might want to add a complete new implementation at runtime, and then this would be handy.
As long as you can decompose your kernel into some set of fundamental operations, in the worst case, arithmetic operations, whatever.
Yeah,
I think you could implement something like that also in the single source model.
Yeah, but then I mean, this is like meeting users where they are. So if you are working with Cutlass, you don't want to do anything else. You want to just use your template instantiation that you know works for your use case and want to throw that in. So
okay, I think you've got lots of questions to get through, so we'll keep going.
Hi. One issue with the approach when it comes to client applications deployment is just the size of a library to begin with, because you include the whole LLVM compiler and a lot of things in there. I think when I last looked at it, it was 100 megabytes or maybe more. Have you looked at how small it could become? Are you making sure you're trying to get it smaller? Do you have any comments on this?
So at this point, we haven't really looked into the distribution issue. We know it exists, but yeah, really nothing I can add at this point. We will need to ship the compiler and the front end, so there's no way around that. We are hoping that in situations where you would otherwise ship a large SYCL kernel library that would become smaller, then you have to just look at the trade-off if it's worth it or not. So
yeah. If you haven't looked at it already, maybe there is room for improvement. So this is a good news. But yeah, that's something to balance with the size of binaries you would generate otherwise. Thanks.
Yeah, I will try to make it short. Just quick comment on what Axel have said. I think I actually know one reasonably big customer which really would like to compile a new kernels from the scratch and not just have some sort of specialization, because it gives users some ability to even write custom kernels. So at least that's one of the customer which are aware and really looking forward to this extension. So just a comment. And another question is that I believe I have tried to use this extension back where it was in naive implementation stage. And back where it was a really hard dependency on having like one API compiler in your path, SYCL headers in your path, and the rest of the development environments, which usually includes, for example, Microsoft headers. Is it still a limitation even these days?
It is. So right now you still need if you think of in terms of packages, you will still need the compiler package because we need the headers and a couple of device libraries to be linked at runtime. But it's also something we are looking at it right now actively. So to make a smaller package to be distributed, probably only including like the header files and the small device libraries that we need, and also making sure that that doesn't need to be system compiler installed on the system. But yeah, it's ongoing work. It's not in the dailies and probably will not be in the first release, but we are looking at that.
Yeah, because I think distribution would be a big issue for anybody who will try to adopt this extension and not be HPC, where you have like user machine and development machine, as we say.
Definitely.
Hey, thanks for the presentation. I would like to know if you have performed some tests against OpenCL and whether those were better or worse in terms of performance, because at least it would really improve the motivation behind this work, since I feel that the approach is quite similar to the one of OpenCL. So
yeah, so you mean performance in executing the kernels or compilation time?
performance and also compilation, like the overall performance, since you're JIT compiling, like.
Yeah, so we didn't look into the performance of the compiled kernels yet because we don't really expect much difference there because it's using the same code base and same compiler frontend. So didn't look into that. For the comparison with OpenCL, so the kernel compiler extension also has a source language for OpenCL, so you can do what was common in or is common in OpenCL. You can do the runtime compilation with the OpenCL source string as well, so that works. I don't have numbers for that in my presentation right now, but OpenCL doesn't have to compile SYCL HPP, so you can probably guess how that would look like. So much faster, but as kernels get more complicated, and I'm coming back to my Cutlass or gem kernel example in general. If the compilation time of the kernel itself becomes larger, of course, the relative overhead becomes lower for that. So, yeah, we really need to do something about the overhead for compiling SYCL in general. So, looking at the headers and speeding that up. But yeah. Otherwise, I wouldn't expect much different between the kernels themselves when they're compiled.
Okay, thanks.
Okay, I think in the interest of time, we'll hold the questions there. Thank you.
Thank you.